Hi, I'm Chris Brown, and this is lecture 2.13 in axiomatic design and manufacturing processes. We're going to look at some of the sort of principles involved in FRs, DPs, and PVs for mechanical parts. So the FRs for mechanical parts relate usually to transmitting loads and displacements, mechanical energy, and consist of different kinds of structures that can transmit load through the structure, and then interfaces that transmit loads between the structures. They might also influence heat transfer, as mechanical engineering includes heat transfer. Scattering. Sometimes you want to scatter or not scatter, reflect spectrally light and sound. So those are other possibilities. And then influencing flow. And so this is to make channels and seals so that you can have valves and have things flow from one place to another. Now, this is not intended to be a collectively exhaustive list, but I think most of the mechanical FRs, the functions, are included here. So there are some, certainly there are some others, and you may have some cause to use those. All right, so the DPs for mechanical parts. Well, certainly shape or form. And then the surface texture, often just called the surface roughness, and there'll be some lectures coming up on that. And then strength, and this would come through the microstructure. So in order to resist some kind of deformation or fracture, it needs a certain amount of strength. And this might be specified by the microstructure, actually. DPs for mechanical parts might have certain kinds of thermal properties. If the FR is to reduce heat transfer, then the DP would be some kind of insulated material. Also, chemical and biological properties. Sometimes things are grown on surfaces, and sometimes you need things not to grow on surfaces, and sometimes we're using the surfaces as a tool in making different kinds of biological or food things. All right, DP and PV. So the DP is a description of a physical component of a design solution. So it's what you put on a print or in a CAD file, or develop in a CAD file. So it might be a part or some feature on it, and it should start with a noun, as we said before. Now, a PV is the description of the process, that is, the application of energy to do work on a workpiece that produces that component or feature. And that would start with a verb, as we saw a couple lectures ago. Now, FRs in manufacturing, the manufacturing process development, they're going to be functional, but not grind. But not grind. But you want to have the function that grinding is going to fulfill, like removing material, modifying a surface. So it wants to be, it should be quantifiable somehow within the functional tolerances based on the customer needs. Here's an example of a poor FR-DP pair. Grind, so XYZ, some part or some surface, and then grinding machine. Now there's a number of reasons why that's not very good, and it certainly is not very illuminating. I'm going to grind this, I'll use a grinding machine, so I haven't really said anything too interesting there. So we might say, what function does the grinding fulfill? So it might be material removal, or to supply some form, or some surface roughness. So we want to think about the function for the FR. And then the grinding is a process. So the FR should not contain, just as it should not contain physical information in manufacturing process development, it shouldn't contain the process information. So the idea is to leave a large design space open in which to find the best design solution. All right, nature of the PVs. So PVs start with verbs and indicate the process and the process parameters. So dP, so that's the process parameters are going to relate to the target value and the tolerances. The dPs are going to supply the physical information required to fulfill the FRs. And the dP, for example, might be a cylindrical shaft and would have a certain length, perpendicularity to the shaft axis, some diameter plus or minus something, and some kind of roughness. PVs are going to be processes like saw, face, turn, mass finish. So here's some examples of the new product development design elements. So you might have a cylinder, you might have threads, the DPs. So now the PVs for the new process development would be turn a cylinder and form threads. So the process solution is found in the new product development process variable. So examples of domain elements here, if we have the NPD to MPD, so the NPD DPs, for example, cylinder and threads, might translate into manufacturer's cylinder and create threads. And so we would like the MPD FR to be solution neutral as well. So in MPD, domain elements, now we're going to go to the DPs. So this might be a turning process or a forming process, and then it could be turn on the lathe or form threads with a tap. So here's a lathe, and there are some. There is a forming tap and a fastener that's been inserted into that. So the MPD, the manufacturing process development, PVs, are the process solution. So if I look at the new product development and the manufacturing process development, of course the PVs could be identical. Work supplied to the workpiece for adding value in both cases. The FRDP in the process development versus the DPPV in the product development. So one could include in the manufacturing could include inspection, production rate, and cost drivers. But the DPPV is just going to focus on the work supplied to the workpiece for adding value, because that's focusing on adding value to the product. Now, it may be useful to work through FRDPPV for the new product development. So you can link all of those and see where you're going to have difficulties, as we've spoken about before, where, say, a DP specification now introduces coupling in the PV to try to accomplish that. So if you do the FRDPPV for the new product development, then you'll be able to uncover some of these problems. And then as the next step, you could go to the manufacturing process development, FRDP space, and introduce things like inspection, production rate, and other cost drivers in manufacturing. Fundamental PVs. All right, so if we go all the way down to the leaf level, what kinds of things do we see in the process variables? Well, forcing some sort of displacement, some sort of deformation. And this has got to happen with some sort of load transfer. So this would be in forming, forging, but also in machining, and although it's not so obvious, we're doing this in grinding as well. One of the nice things about additive manufacturing is it's very lowly loaded. Okay, another one would be heat transfer. So supposing we're trying to melt something or give it a certain heat treatment, remove the residual stresses, I get some sort of composition in the surface, so where we would do carburizing involving both heat and mass. All right, so these are sort of fundamentals all the way down at the leaf level. So we've got displacement, we've got heat, and we've got compositions for changing. So we could also look at their time derivatives. And so we could look at displacement rate, like velocity, or even the second derivative, the acceleration that is necessary to form some parts. So there we have rate of heat transfer and rate of mass transfer as time derivatives. Now, commonalities, as we spoke about in the previous lecture, can be found in some of the basic sciences. Generally thinking physics, chemistry, material science, also biology, depending upon what you're trying to manufacture. And so we should note this in the literature search, and particularly in the cases where you don't find enough in the literature in the manufacturing literature. So then you might want to expand into basic physics and chemistry. So shape to form and waviness. Now this is a question of scale, and we'll talk about this later. Actually, it's a geometric continuum from the large scales at which the form is evaluated to the very fine scales at which we're looking at roughness. So we can think of this as being one continuum of geometry, but then we somehow put scale boundaries on it, and this is explained in the standard, ASME P46.1, for example, where the standard boundaries would be depending on how you wanted to fix that, what you thought the functions were. But there's relatively little guidance on this, and we will take that up in a later lecture. Let's just consider coupling at the surface now. And it's note that it is difficult to modify the surface roughness without modifying residual stresses or maybe the microstructures and possibly the composition as well. Now, the thing to keep in mind is that when we go to modify the surface, it is often inherently coupled, and we have to watch out for these other things that could result in unintended consequences. And so if we can apply the axioms through the decomposition from FR, dP to PV and all the way down the hierarchy, we should be able to take care of some of these things and try to change the way we're doing it before we actually get there. Anyway, thank you very much for your attention.